We are going to talk about section 4.2, which is all about Riemann sums. And Riemann was a mathematician who lived in the 1800s. He was German. Lived from 1826 to 1866. So he lived only 39 years, actually. His birthday made it 39 years. But these ideas became foundational for being able to define area under a curve. And his idea was to slice things into small rectangles so that you could estimate area under a curve. So we call these little rectangles and the sums of their areas Riemann sums. Okay, so here's the main idea of what we're going to do. There's all sorts of contexts where we're interested in finding the accumulated area under a curve. One of the most common, and one we've talked about already, is velocity. Say we're in miles per hour, and here we're counting hours on the horizontal axis. And say that this area here under this part of the curve was equal to 10, so you're going to add all those up. Here, this area is 4. Going to add up all that area, and say we somehow knew that this area was 2 under this, between the curve and the horizontal axis. So we do talk about net distance as opposed to total distance. Net distance is also displacement. So here net distance or displacement. It's like where are you from where you started. And here you would be 10 minus 4 because you went backwards, or down 4 plus 2. So that would get you back to 8 miles in this case. And if we were interested in total distance, this is like your car's odometer or your step counter on your watch. It's keeping track of how far you've gone regardless of what direction you're going. And in that case, that would be 10 plus 4 plus 2, and that would give us 16 miles. So you've gone 16 miles, but you're only 8 miles from your starting point. So the important thing that I want to emphasize is we don't always have to be talking about velocity and then counting up distance. We say that this was actually like beats per minute, like a pulse. Beats per minute. These numbers hopefully wouldn't be true, but say that somebody's pulse was being charted as beats per minute over a certain number of minutes. And then this would count, you know, the area under a curve wouldn't be counting distance, but it would be counting, so here the area would be counting total beats, total heartbeats. So the idea is if you're given a certain rate, you know, over a time or over something that you're counting, keeping track of, then you can accumulate or count up the total number of beats or miles or dollars or calories by counting up the area between the curve and the horizontal axis. So if you've got a rate that you know certain information about, like this rate behaves like this, then the accumulated area between the curve and the horizontal axis will be counting things for you. For example, velocity, if you have a curve that's representing velocity, if that curve represented velocity, and you found area between the curve, you know, under the curve or between the curve and the horizontal axis, you would be counting up all your total miles. If you had a curve that was counting pulse, your beats per minute for a pulse, then the area of the curve between the curve and the horizontal axis will be counting, you know, those number of beats. Of course, you wouldn't have negative beats in that case. If you had a curve that was representing your wage, again, you wouldn't have a negative wage, but maybe your wage was something like this, and you wanted, and so that's measured in dollars per hour, and you wanted to find out how many total dollars you were going to be making, then you add up the area under the curve. So this is the idea that the rate, if we want to find you know, the accumulation of the thing that the rate is counting, then we take the area between the curve and the horizontal axis. Another one might be say you're exercising and you know you're going to burn a certain number of calories per hour, and you have a curve that describes how many calories per hour you're burning. If you added up the area under the curve, you would get those total calories that you've burned. Four common ways that Riemann sums are used. There is a left-hand sum, a right-hand sum, a midpoint sum, and a trapezoidal sum. For a left-hand sum, say that we wanted to estimate the area between A and B, area under a curve, we're going to use rectangles like Riemann suggested, and we're going to look at, in this case, this interval, this interval, this interval, this interval, and we're going to make 4 rectangles, always using the left side of the rectangle to determine our height. So here our height would be that high for our rectangle, and then for this interval here, the height, we go to the left part of the interval, and where that left x value is on the curve, evaluated on the curve, that is the height of our rectangle. And so same here for this this interval here, we go to the left endpoint and we'll go up high just till we hit the curve, and then that will be our rectangle. So we get this height of a rectangle. And then for this one, so these are left-hand Riemann sums. For a right-hand Riemann sum for the same curve and same number of intervals, we've got these 4 intervals here. For each interval, we go to the right side of the interval, and that will determine the height of our rectangle. So here we go there to that right one. So I'm really just focusing in on the right side of the interval where it is on our function. And those will be the heights of the 4 rectangles in this case. So this right-hand Riemann sum is definitely going to overestimate the area under the curve, but it's just an estimate. So this was a right-hand Riemann sum. It is an overestimate. We're catching area that really isn't under the curve. And this left-hand sum happened to be an underestimate. We were missing some area that should have been under the curve. That doesn't always happen with left and right Riemann sums. I'm sure you can imagine that if you had a curve like this, the left Riemann sum will overestimate. And then you always have curves that are wonky like this. And so some left-hand sums are overestimating. Some left-hand sums will underestimate. Okay, the next one is called a midpoint sum. So for a midpoint Riemann sum, you're going to evaluate the height at the midpoint of each interval. So if our first interval is from this point here to this point here, we're going to evaluate the height of the rectangle. Where does that midpoint of the interval hit the function? And that's what we're going to use for our height. So for this interval here, we would find the midpoint, and that is going to be the height of our rectangle. So the midpoint of each interval is what we use to evaluate the function, and that'll be the height of the interval. So this one would look more like, let's see, that's about right there. And then for this next interval, the midpoint hits the graph right here. And we have a rectangle like this. And our last one, the midpoint hits about right here. You can see that the midpoint Riemann sum is so far the most accurate of the 3, because even though we're overestimating here, we're underestimating a little bit right here, so it's almost canceling each other out. So midpoint is a good estimate for Riemann sums. And the last one is trapezoidal. And so you can see with this one, each area that we're counting is not a rectangle anymore, it's a trapezoid. These do tend to be the most accurate of the 4 ways. And so we're going to remember that the area of a trapezoid equals the average of the bases, so 1/2 base 1 plus base 2 times, I don't want to say height, maybe we should say width here. So this is base 1, base 2, and this is our width. So take the average of these guys, this base, this base. So for example, if I had a trapezoid that was 4, and this length was 7, and this was 2, the area here would be 1/2 of that 4 plus 7 times 2. And so that is 11 halves times 2, which is 11. So this would be the area of this trapezoid here. Okay, we've talked a lot about the theory of Riemann sums. We need to get into some concrete examples, but we do have just a teeny tiny bit of theory to still talk about. So the whole topic of Riemann sums, a big part of it is talking about the different types. We just talked about those. Another thing that comes up when you're talking about Riemann sums, though, is something called sigma notation. Sigma notation is used a lot of places in mathematics, not just Riemann sums, but it is a part of the theory and the ideas behind Riemann sums, so we need to talk about what sigma notation is. It's possible you've seen this before, hopefully, in an algebra class, but sigma notation just makes writing really long sums easier. And so you can imagine, if you had a curve and you were doing a Riemann sum and you had, say you had like, 50 rectangles that you were going to use to estimate the area under that curve. Sigma notation is going to allow us to write it much more concisely and just more efficiently. So the Riemann sum looks like, well, the sigma notation, looks like the Greek letter sigma, which signifies adding things up. We're summing things up. We're adding things up. Whenever we see this notation in mathematics, we think about we're about to add some things up. And this notation is used, one of the first things that you will encounter is a starting point and a stopping point. So down below the sigma usually is written a place where you're going to start your counter. And right above the sigma is a place that you're going to stop your counting. So I equals, this is going to be a starting point. And then up here we write where the stopping point should be. We're indexing something, we're counting several similar things. And then the thing that we're actually adding up goes here. And sometimes it's a formula, more often than not, thing you're adding up. And you'll see some I's in here. Okay, let's try a concrete example. Say that we were presented with this object here. It is sigma notation, so this tells us we're about to add up a bunch of things. This tells us where to start. This tells us where to stop. And this is the thing that we keep adding up, I squared. So at first, I is 2, so this means this is 2 squared. And we're going to stop when we get to 7, but until we get to 7, we just go on to the next number. So this is plus 3 squared, we're adding 4 squared, we're adding 5 squared, 6 squared, and 7 squared. So this particular example doesn't have anything to do with Riemann sums. It only has to do with sigma notation. But this gives you an idea of the different pieces of this. So let's now look at an example which uses Riemann sums and sigma notation. Okay, they're asking us to represent the left Riemann sum with n equals 6 rectangles. This is very typical of how they'll describe how many rectangles they want in the Riemann sum. They'll tell you n equals 6 or n equals 4 or n equals 20 or n equals 100. N equals 6 rectangles of, and here is our function. This is the curve that we're interested in, and it's going to be on this interval 1 to 3 using sigma notation. Let's get a picture of the curve. That'll help us be able to make these Riemann sums and using the sigma notation. And this curve is actually mostly under the x-axis for the part that we're interested in. So it looks like this. It's kind of a parabola that's sort of flattened out. And we're looking from 1 to 3. And we're going to have 6 rectangles. Okay, so let's write the parts we know. We know we're looking for a left Riemann sum, so that's indicated with an L, and then often you'll put the number of intervals just as a subscript. So the left Riemann sum with 6 intervals, and we're going to write it using sigma notation. And we are adding up a bunch of areas of rectangles. This is, well, let's back it up a little bit. So we're adding up area of rectangles. We're going to make 6 different rectangles in here, and we're going to add them all up. But the rectangles are, the area of the rectangles are going to be found by a certain height times a certain width. And we're going to have an index. We don't know yet what to put here or here. So let's draw the picture of what's happening, and then we can refine what our sigma notation says. So in here, I'm going to have 6 divisions. So it looks like this. So we'll have 1 interval, 2, 3, 4, 5, 6. And these will be all equal width, sorry. We're going to call these, common way to describe these intervals are, we look at x0, x1, x2, x3, x4, x5, and x6 as the x values that are delineating those intervals. So if we're looking for a left Riemann sum, that means this left part of the interval, we're taking that y value of the function. Again, this is the function f of x equals 0.4x squared minus 5. And then we'll take this one, and then we would take this one, and so on, all the way down. So we're going to have 6 rectangles. And here's the last one right here. Okay, so it looks like this Riemann sum, this L6, the width. First, let's figure out what the width would be. Well, we have an interval that is 2 units long. That's 3 minus 1, and we want to divide it into 6 different intervals, and so that's 2/6 or 1/3. So each of these intervals right here are going to be 1/3 in length. And this is typical of how we'll find the length of the interval, of each subinterval, is you take the length of the whole interval and divide it by how many subintervals you want, and that will give you, this is a third, this is a third, this is a third. Each of these has width 1/3. So that's definitely this part here. So that's going to be the 1/3 shows up here. And now the height of each of these. Well, the height of each of these is different. It's dependent on the function evaluated at a certain point. It's going to be the function evaluated at x naught, the function then evaluated at x1, x2, x3, x4, x5. The function never gets evaluated at x6 because it's not a left-hand side of any interval. So we're going to take the function evaluated, and for right now we'll call it xi, and I is going to go from 0 to 5. And this is it. This is representing the Riemann sum with 6 rectangles of that function on the interval 1 to 3 using sigma notation. We've said this is going to count up 6 different intervals, and these are exactly the places that we want the y value to be. This is the width of each interval. So we start at fx0 for a height, then fx1, and keep going. Okay, so this next example, we are still representing Riemann sums with sigma notation, but this time we have a right Riemann sum, and this time the number of rectangles changed to 8, so they want a sort of a finer view of things. So we're just going to copy this guy here and put it down here, and we'll change it a little bit. Okay, this time we don't want left Riemann sums, we want right ones, so I'm going to take away these rectangles here. And we also have a different width and number of intervals. So these intervals here will no longer work. These were only when we wanted to split things up 6 ways, but now we want to split things up 8 ways into 8 subintervals. We can still start and stop at 1 and 3. Let's figure out, well, we can draw them without figuring out the width first of all. Here's a 2, and I need to split everything up into 4 pieces. Okay, so I think we've got our 8 subintervals. We're going to make them all equal width. So this time we're going to have a right Riemann sum with 8 subintervals. And first of all, let's figure out, well, fx of some I, we'll have to figure out with a starting and stopping point, but let's figure out the width here. Let's see, we're going from 3 to 1, so the width divided by 8 intervals, or divided by 8, yeah, and the interval length is 2. We're going to divide that by 8, so it looks like each subinterval needs to have width 1/4. That makes sense, so each of these has a width of 1/4. So the 1/4 goes here, that's the width of each rectangle, and the height of each rectangle is f of x sub I. We have to figure out which xi's we're talking about. So if we still call this one x0, x1, x2, x3, x4, x5, x6, x7, x8. Now this time we're going to use, for each interval, we're going to use the right side. So this is the first rectangle that gets counted here. And here's the second one here, and so on. We'd have more rectangles. But importantly, the first rectangle used the height of x1. So this started when x equals 1, and it goes up. The last rectangle will use the right side, so it'll be, where is the function evaluated at x8? For a right-hand Riemann sum, we always have to use the right part of the rectangle, the right endpoint of the rectangle. And so we never actually use x0 as a height for a rectangle. It's just all the other guys, x1 to 8. And so this is how the Riemann sum would be represented in sigma notation. So just note the differences between this guy and this guy. First of all, there were 8 intervals here. And here we had to start at x0 and go up to x5 for our heights of our rectangles. But here we started with x1 and went up to x sub 8 for the height of the rectangle. This example, we're actually calculating a Riemann sum, and we're going to calculate a midpoint Riemann sum for the same old function that we've been working with in the same interval, and we're going to use 4 subintervals. So this time there's no mention of sigma notation. It's just they want us to calculate the sum, the Riemann sum. So in the end, the answer needs to look like just a number. We want the estimate for the area under the curve. So in this example, we start out knowing that we're going to have 4 subintervals. So our subintervals will look like this. And what is the width of each subinterval? It'll be the width of the total interval, that 3 minus 1 from 1 to 3, divided by the number of intervals, and so that's 2/4 or 1/2. This will be the width of each of our subintervals. And then the height, so we're going to go right at the midpoint of this first interval between 1 and 1.5, because this right here is 2. So between 1 and 1.5, we're going to evaluate the function. And this will be the rectangle that we want to find the area of. Then we'll go to the midpoint between 1.5 and 2, which is 1.75, and we'll evaluate the function there and use that as the height of our next rectangle. Then we'll go to 2.25, and where it hits the graph is where our next rectangle will be, the height of the next rectangle. And then it looks like at 2.75 we choose that point to evaluate the function at for the height of our next rectangle. So this is our midpoint, and it is going to be a fairly good estimate because even though we overcount over here, we're undercounting here, we overcount a little and undercount a little. So they're almost, it won't be exact, but they are doing a better job than the left and right hand sides. Okay, so let's figure out what we need here. We're getting a midpoint Riemann sum with 4 subintervals, and this will be let's just do this first rectangle here. The width of this rectangle is 1/2, and the height of this rectangle is the function evaluated at 1.25. So 1/2 times the function evaluated at 1.25. This was the midpoint between 1 and 1.5, that first interval. And then to that we'll add 1/2, so that's the width of the second interval, and then the height of this interval will be the function evaluated at 1.75. And then 1/2 times the function evaluated at, looks like 2.25, and 1/2 times the function evaluated at 2.75. These are all numbers that we can find, and so we can actually, each of these terms has a 1/2, so it will be faster just to pull that out and then evaluate each of these where the function is, and we'll go to Desmos to find that out. So here's our function 0.4x squared minus 5. I'm going to restrict it to 1, from 1 to 3, just to see what part. Okay, so this is actually, it's a little more, steep than I have it drawn, but we're interested in the area between this curve and the x-axis. And so we'll make up a table, add a table where we're interested in x and f of x. And we'll let x, remembering that we want to calculate at 1.25, and then at 1.75, and then 2.25. These are all the midpoints of those intervals, those subintervals. Okay, so we're looking at negative 4.375 minus 3.75 minus 2.975 minus 1.975. So negative 13.1. That is the estimate for the area between the curve and the x-axis. So we just found out that adding up each of these values of the function at these 4 points was equal to negative 13.1. Guess we don't need this guy quite so far. So 1/2 times that negative 13.1 is going to give us a negative 6.55. I will tell you that the actual area between the curve and that horizontal axis from 1 to 3 is negative 6.533 repeating. So we don't know how to do this yet, how to find the real area, like if we were just to find, the curve, follow the curve exactly and find this area. We're using Riemann sums just to estimate it, but we can already see that this estimate is actually pretty good. With that midpoint estimate, we got a negative 6.55. The actual area between the curve and the horizontal axis is negative 6.533. So this midpoint Riemann sum is a pretty close estimate. Okay, let's just pause here and talk about the width of subintervals. Say you're asked to use n equals 20. So we want 20 subintervals on this interval. This is the larger interval. What would the width of each subinterval be? So you'll often see this written as delta x or delta t or delta something. This is the width of each subinterval. And this is going to equal, in this case, it's 7 minus a negative 2 over 20. This is the length of the whole interval. And this is the number of subintervals that we want. So in this case, it would be 9 over 20. So 9/20ths would be our delta x. That would be the width of each subinterval. For our last example, we've got a new function, f of x equals x squared over x plus 1, and we're going to find the trapezoidal sum this time for n equals 5 on the interval 1, 3. So let's get an idea of what this looks like. Here's 1, here's 3. And this particular function looks something like this. That's a terrible drawing. It's more like this. Okay, so we're interested, starting here, stopping here. It is not linear. It looks kind of linear, but it's not. And so we want to calculate the area between the curve and the x-axis here. And we're going to use a trapezoidal sum. So let's start by thinking first, what is the width of our subintervals? So they tell us that we need to use 5 subintervals. That's not awesome because it's not really an even number, but we need to do 1, 2, 3, 4. So we need to have, we'll find equal width 5 subintervals. And the way that we'll find that, the width of each subinterval is delta x will be 3 minus 1 divided by the number of intervals. That's 2/5, or 0.4. This is the width of each subinterval. So this point here would be 1.4. This point here would be 1.8. This here is 2.2. And this is 2.6. And so we are going to use trapezoids. So we'll use both endpoints. They're not rectangles anymore. It's going to be a trapezoid each time, and we're going to do 5 of them. So you have to remember that formula for a trapezoid. So this will be the trapezoidal sum on 5 subintervals. The width of each interval is 0.4, so 0.4. And then this first trapezoid, we have the 0.4, and now we have to take the average of these two heights here. And so that will be f of 1 plus f of 1.4 divided by 2. This is just the first trapezoid. Then the second trapezoid will be a width of 0.4 times, now we're going to have an average of these two legs here. We've got our width of 0.4, and then we need f of 1.4 and the average of that, and f of 1.8. So f of 1.4 plus f of 1.8 divided by 2. So just again, this is a formula for the area in a trapezoid. It's that width times the average of the heights. So width times the average of the heights, and we've got 2 of them. We need 5 of them, so I'm going to have to scoot things over a little bit. Okay, so here is the second trapezoid. And we'll just get the next 3 pretty quickly. This will be plus 0.4 times the average of f of 1.8 plus f of 2.2 divided by 2. This is the area of the third trapezoid. And we're going to keep adding to it. Plus 0.4 times f of 2.2 plus f of 2.6 over 2. And the last one, 0.4, that width, times, for this last one, we're going to get this height, which is f of 2.6, and f of 3, they're the average of those two, so we'll add them up and divide it by 2. F of 2.6 plus f of 3 divided by 2. So here we've got the area of the fourth trapezoid, and here is the area of the fifth trapezoid. This is a lot, and we don't want to make any mistakes as we're going, but we have all the pieces we need. We'll just throw some things into Desmos to evaluate it. Okay, so here I have my function x squared over x plus 1. I am going to restrict it just so I can see what's going on between 1 and 3. Whoops. Okay, this looks like it's linear. It's not. It does have a little bit of a curve to it, but I want to get the area under this, between this curve and the x-axis. So we'll just say we want to add up 0.4, and 0.4 is going to get multiplied by each of the 5 terms, so I'm just going to put it once outside the parentheses. And then I have f of 1 plus f, plus f of 1.4, and I'm going to divide this by 2. That's the average of those two heights, plus f of 1.4 plus f of 1.8, and then I'm going to divide that by 2, and then interesting that we're getting an undefined. I'm not sure why. Let's see what's causing that. I realized what was causing the undefined. I was asking it to restrict the function from 1 to 3, but not including it. So we'll include 1 now, and we'll include 3. You can't evaluate something if it's not part of the domain. Okay, so back to where we were, plus f of 1.4, and we'll divide these by 2. Keep adding. We have 5 trapezoids we need to do, plus f of 1.8, and we will divide those by 2. And whoops, plus needs to go out here, plus f of 1.8 plus f of 2.2, and taking the average of those. We've got 3 trapezoids so far, f of 2.2 plus f of 2.6, and divide those by 2. And then we have the last one, plus f of 2.6 plus f of 3, and divide those. This is the average of those two heights. Okay, so we've got 2.69, and this is the whole Riemann sum because we multiplied it by 0.4 in the beginning. So 2.6956. So this trapezoidal estimate that we got is 2.6956. This is our estimate for the area between the curve and the x-axis from 1 to 3 of this function. The actual area, if there were no gaps and we were following the curve exactly here and we found the real area under here, so actual area is 2.6931. So again, our estimate is pretty good. Trapezoid is definitely proving to be the most accurate. We don't know how to do this yet. We will learn soon how to do the actual area, but for now we're just practicing these different ways to get Riemann sums, which are best estimates. The last thing I want to do in this video is show you, this is a website where you can compute Riemann sums. Here we're going to compute a right endpoint of this function here, and we have n equals 10 subintervals, and we find that the estimate is 4.90595. We're definitely missing some area, like right here there's a big gap, here is a big gap, here we're overestimating a little bit, and there's some more gaps here and here. But if you took a left endpoint, it would look like this. And if you took a right or a midpoint Riemann sum estimate, it would look like that. This one doesn't have trapezoidal, it just has left, right, midpoint. You can actually take, somewhere random in the middle there. But this shows us, the difference between a left endpoint estimate and a right endpoint Riemann sum. It also shows us if we decreased the number of intervals, it gets more blocky and less accurate. But if we said take n equals 30, then the estimate gets a lot more accurate. And even if we went higher and higher, this value of the Riemann sum that we're finding right here, the 6.47, this number, the integral, is the actual area under the curve or between the curve and the x-axis. So these are not too far off. So the number of subintervals you take definitely will affect your estimate. And sometimes a left endpoint is better than a right endpoint, or a midpoint is usually pretty good. So I'll include this a link to this in this assignment so that you can mess around with it too. You can also change the, we could do the one that we were doing just a minute ago, x squared plus 1. No, is that what it was? No, just x squared divided by x plus 1. And we could go from, you can change the endpoints from 1 to 3. And if you're doing a left sum with 45 subintervals, you're getting pretty close. Less subintervals, your estimate's not going to be that awesome. All right. So this trapezoidal sum was the last of the 4. We talked about trapezoidal, midpoint, left, right. We also talked quite a bit about sigma notation, and that is a notation that follows you throughout calculus. So we didn't use it a whole lot here, but we do want to get comfortable with it, and Riemann sums are a perfect context for practicing sigma notation. It'll come up again in calculus 2, and it comes up in a lot of different math applications.